Alright, here's the video guide for lesson 10.2.1. Like I said in my daily announcement yesterday, we are moving into 10.2, which is now going to move past circles and back into probability like we were studying in chapter 4. We're going to really focus on more of that area model here today. And the idea is to learn more about conditional probability. What does that mean? How does that play into this? And the idea of two events being independent from one another. Again, two things we don't know, but we'll hopefully discover throughout the lesson. And I want to just get right into it because there's a lot of vocab, and as we work through it, a lot of this idea of conditional probability and independence will make more sense to us. So I'll read the intro because the intro is kind of important. When two events can occur either simultaneously or one after the other, how can you calculate the probability of one of them when you know that the other already has happened? You will investigate this question today. Then you will see how finding conditional probability will help you determine if two events are independent of each other. So like the idea really behind this is like, what if we know one event already happened? Is that going to change the probability of the second event happening? And we're going to see if those two kind of are independent of one another. So got to kind of read the problem here too to understand what the game is. Maribel is playing the board game 8 the hard way with her friends. Each player rolls 2 dice on their turn and moves according to the sum on the dice. However, if a player rolls 2 4s, called 8 the hard way, they instantly win the round and play a new round and a new round is started. Shayna stepped in the kitchen to get a snack and heard Maribel shout, "Woohoo, I got an 8." Shayna knows that Maribel got an 8. With your team, help Shayna investigate the probability that Maribel rolled 2 4s and won the round of play. In other words, calculate the conditional probability that Maribel rolled 2 4s, given that you know she already rolled a sum of 8. So this is going to introduce that idea of conditional probability because we know that she rolled a sum of 8, but we don't know if she rolled 2 4s. So we know an event already happened, but what's the probability that she actually rolled 2 4s, sorry. So when we start with A here, it says we want to use an area model, this thing over here, to represent all the possible sums of the numbers when 2 dice are rolled. Can't talk. All right. So this on the left side is going to be dice number 1 being rolled, and up here is dice number 2 being rolled. And I'm just going to fill out this area model. So if 2 1s are rolled, that's a 2. This is 3, 4. So I'm really just calculating the total here of these dice being rolled. 1 and a 1 would give you 2, a 1 and a 2 would give you a 3, a 1 and a 3 would give you 4, and I'm just going to work through this whole chart here. So this is 5, this is 6, this is 7, and I'm actually going to do some editing here, and I'm going to fill out the whole chart. The whole chart is filled out. 1 and a 1 gives me 2, a 1 and a 2 gives me a 3, and this is the whole sample space for this entire game. All the different possible number combinations you could rolling these 2 dice. All right, so now we got A done. We filled out the chart here, and we can go on to B. So however, since you know that Maribel rolled a sum of 8, the sample space is now changed. This whole thing used to be our sample space, but now that's changed because we know that she has rolled an 8. So on your area model, shade all the ways a sum of 8 can be rolled, and then how many different ways can a sum of 8 be rolled? That is, how many outcomes are in the new sample space. So I'm actually going to use my highlighter here, all the different types of 8s. You could get an 8 here, an 8 here. This whole diagonal here could be an 8. And so I got to extend my page a little bit so I can keep working on this. For B, our new sample space is really just a sample space of 1, 2, 3, 4, 5, because there's 5 different outcomes that will give us a roll of 8. All right, and that's what that question's asking. So it said our sample space has changed. How many different ways can the sum of 8 be rolled? Well, it can we could roll an 8 5 different ways. All right, well, we'll go into C here. You are interested in the event of 8 the hard way, which means you have to roll 2 4s. How many different ways can 2 4s be rolled? Well, there's only one way that 2 4s can be rolled. If you roll a 4 and another 4, you would get an 8. So there's only one way that you can roll 2 4s, and that would be to get a sum of 8. Okay? So that's the part C. We shrunk down our sample space in part B because we know that there's only 5 possible outcomes to get an 8. And then in part C, it just asked us how many different ways can 2 4s be rolled. Well, they can only be rolled one different way. And so we go to D, and it says, what is the probability of the event 8 the hard way, given you know that she already rolled a sum of 8? Well, there is a 1 in 5 chance that she rolled 8 the hard way, because we know she rolled all 8s, or no, we know she rolled an 8, and there's 1 in 5 of these 8s is 4 and a 4. And so we say that to get 8 the hard way, knowing what we know, she has a 1 in 5 chance that that she actually rolled it. And so that's the part D right there, and we'll go to part E. And that's really the introduction of kind of conditional probability there in part D. We were given that she rolled an 8, so our sample space then changed. And then we said, well, 8 the hard way, there's only one way to get 8 the hard way, and our sample space changed to 5, so we say it's a 1 in 5 chance that she actually rolled it. And then in part E, it changes just a little bit, and so it says Becca rolls high, which means that she rolled a number of 9 or more. What is the conditional probability that she rolled an odd number, given that you know she rolled high? So again, we are given this information, which makes it conditional probability. And so I'm going to highlight all the numbers that are, and I'm going to change the color. I'm going to highlight our new sample space, all the numbers that are technically a high number. And so she had a 9, all 9s would count. 10s would count because those are high, 11s, and 12s. And so our new sample space here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our new sample space here for D, and I got to change back to my pen, or sorry, for E. Ooh, that looks nice. I didn't mean to grab the calligraphy pen. It's going to be something out of 10 because 10's our sample space. And then it asks, so our sample space changed to all the high numbers. And then it says, what is the probability that we know she rolled a high number? What's the probability that that number is odd? Well, now we just count all the odd numbers in that sample space. So you have 1, because 9s are odd and 11s are odd. You have 1, 2, 3, 4, 5, 6. So you have 6 out of 10 chance, because you know that 10 is coming from, you know that there's 10 numbers in the sample space of a 9 or higher, and 6 of those 10 numbers are odd. So there's a 6 in a 10 chance that it is an odd number, knowing that she rolled a high number, which means 9 or more. All right, and again, that's an example of conditional probability because this is our entire sample space, and we were given a new sample space. We were given a sample space called the high numbers, which was all the numbers 9 and above. And then when it asks us, well, you know, what's the probability of her getting an odd number in that new sample space? We just say that we count all the odd numbers in our new sample space, and in our case, that was 6 out of 10. All right, we'll continue this work with conditional probability in this next problem and get into the idea of independence. Okay, this one is a little bit more, it starts off kind of like probability problems we've seen before. And so we just have this table here. We have engineering majors and other majors. We have lives off campus, lives on campus. And so we have our total sample space here. And it's going to change depending on what they're going to give us. And so the first one, it's going to ask us, what is the probability of a student just living on campus? All right. Well, the people that live on campus, there are 6 engineering majors living on campus and 34 other majors living on campus. And so that tells me that there are 40 people, for part A, sorry, there are 40 people living on campus, and then our sample space hasn't been shrunk yet, so we got to take into account everybody. And so what we do is we need to add up everybody that we know in this sample space. So 6 plus 30 plus 170 plus 34. And if you add up everybody, there is 240 people total on campus, off campus, engineering majors, other majors. Total people, 240. And 40 of those 240 live on campus. And so we've answered our question of what that probability is that a student lives on campus. It is 40 over 240, or if you reduce it down, that's 1/6 of the students total students live on campus at ETU. Okay. Now we're going to move into B, C, and D. It's going to get a little bit more picky, and we're going to shrink down our sample spaces. So we copy the table, already have it right here, and shade the cells with engineering majors. And so I'm actually going to shade that again with my highlighter. We're going to shade these two because those are my engineering majors. What is the conditional probability of a student living on campus given that you know the student is an engineering major? Well, if that's going to change our sample space, because now we're going to forget about these other majors and we're just going to focus on the students that are engineering majors. And so for part B here, we know that there are 36 total students in our new sample space because there's 36 engineering majors on at this school. All right. And then it says, what is the conditional probability that a student is living on campus, knowing that they're engineering majors? And so there are 6 students that are living on campus that are engineering majors. And so we say 6 out of those 36 engineering majors are living on campus. And if we reduce that down, that is 1/6 of the students. 1/6 of the students are following this conditional probability. They are engineering majors that live on campus. Okay, again, conditional probability because we've shrunk down our sample space to just the engineering majors here. All right, and now we're going to get into part C. It's going to bring in this idea of independence, and I'll try to explain these fancy math lingo that they use here. So it says 2 events, A and B, are independent if knowing that B occurred does not change the probability of event A occurring. That is, 2 events, A and B, are independent if A given B, meaning the conditional probability, is the same as your just regular probability that A would occur. Meaning that, in our case, if we know that students live on campus, does that change? If we know that they're engineering majors, does that change the probability that they live on campus? And if it doesn't, then those two are independent of one another. So then that's kind of the question they're asking. Are the events living on campus? That would be event A. I don't know if I'm on my pen or not. That would be A, living on campus, and B, engineering majors. And we're going to try to see if those 2 events are independent of one another. Well, we know that the probability of just living on campus, so P of A of just living on campus. So I got to go down here, see the probability of A happening, or just A means, again, representing that they live on campus, is 1/6. We got that because when we looked at the probability of living on campus, it was 40 out of 240 chance that you live on campus if you go to this school. And then if we look at probability of living on campus, A, given that we know that they are engineering majors, B, we also said that was 1/6. And what this is saying is since P of A, the probability that they live on campus, is the same as probability that they live on campus knowing that they're engineering majors, now that we know in our case that these 2 are equal, that we know these 2 are independent of each other. So these are independent of one another. Independent. Again, because the 2 probabilities are the same. Right here we knew that 40 out of the 240 live on campus just in total. We know that from part B that there's 1/6 of people that live on campus that are engineering majors. And so when we are looking at these 2 events, we know that they're independent of one another because they equal the same thing. All right. Now we got to get into mutually exclusive. I will do this one. I'm looking at my time. I'm going to run out. So I will do part D and the last problem in the second video.